Hi everyone, welcome to our video on a related rate problem involving a right triangle and a ladder. Right now I'm just on the screen where we would have our procedure lined up for us, where it's like this 4-step process, and we're going to break it down. So let's go to it. All right, so we've got this problem here. It says a 10-foot long ladder is leaning against a wall. The bottom of the ladder is sliding away from the wall at a rate of 4 feet per second. Find the rate at which the top of the ladder is moving down the wall when the bottom of the ladder is 8 feet from the wall. All right, so we see there's definitely geometry involved, and we want to get a picture going. All right, so step one, picture. All right, so we've got a ladder. Here's our wall, and here's the floor. And we've got a ladder leaning against it, something like that, and I'm just putting dots down to really show, hey, there's a triangle. Okay, so there's my ladder leaning against a wall, and I've got the bottom of the ladder is sliding away from the wall. Okay, so let's put this in red. So the ladder is sliding away from the wall. All right, so that means it's going that way. It's sliding away from it at a rate of 4 feet per second. Okay, so we'll underline that too. We'll make sure we know what that represents real soon. And then it's saying find the rate at which the top of the ladder is moving down the wall. So moving down the wall would mean that it's sliding down that way when the bottom of the ladder is exactly 8 feet from the wall. All right, well, with my picture, I'm going to do my variables. So from the base of the wall to the base of the ladder, I'm going to call X. And then from the top of the ladder to the floor, I'm going to call Y. And then our hypotenuse, so it is a right triangle, or we assume it's a right triangle with the wall being vertical and the floor being horizontal. Our ladder itself is the hypotenuse, but I'm going to label it Z. So often it's a good idea to just make a picture with only variables. So picture with only variables so far. With only variables. So notice I'm not putting in any numbers. And these in the blue and red, I can say what they are. So if this is our X length. It's changing though. This red is showing it's changing, which is showing the ladder sliding at a rate. Let's go ahead and underline all of that. Rate of 4 feet per second. So the rate at which X is changing is what this is describing in red. This is dx dt. And then the blue, well, that would be the rates at which y is changing, so that would be dy dt. Okay, so we have these. This is all variables. Okay, so that's useful for us. And then maybe let's also get a picture with numbers involved. Picture with numbers. So I'm going to do that separate. You could put them here, but I usually like to just do them separately. And this one, I'm just going to draw just the triangle. And then let's put down what else they said. So they said a 10-foot long ladder is leaning against the wall. Okay, so that's 10. And then it says the bottom of the ladder is sliding away. Well, I marked that in red. I'm going to keep that just labeled for now as red, what I currently have. And it says find the rate at which the top of the ladder is moving down the wall. Okay, so we have that in blue. When the bottom of the ladder is 8 feet from the wall. Okay, so bottom of the ladder, 8 feet from the wall. Okay, so this that I'm underlining in the black ink is for this picture with the numbers. And then look at this. If I have a right triangle, I can use Pythagorean's theorem. A squared plus B squared equals C squared to find any missing side. So remember, if you ever have a right triangle, you have Pythagorean's theorem to help you. Okay, so right triangle, Pythagorean's theorem. And so let's use this to find this missing side. So let's go ahead and say, hey, this is our A. The hypotenuse is O, we see. And so the missing side is B. And so we have 8 squared plus b squared equals 10 squared. And then 8 squared is 64, so 64 plus b squared is 100. We'll subtract 64, so we have b squared is 36. And then we can square root both sides to give us 6. Now when I square it, usually we do plus minus, but because this is a physical application, I know that it should not be negative. So I know this b is really 6. So I'm just going to kind of cross it out at this point and just say, hey, this is 6. And let's get rid of these letters. So I only wanted that for the Pythagorean theorem. And at this point, it's kind of a distractor, I would say. And I've got my numbers ready. Okay, so I have my expression with the letters, and I have it with the numbers. And I chose to do 2 separate ones. You could do them in one. And what we will need to do is kind of combine them somewhat at one point. Okay, but I have my picture. Step 2 is I want to think of an equation that can be used to help me. Well, it is Pythagorean's theorem again. Pythagorean theorem with the variables that I chose, though, with my variables. Okay, so Pythagorean's theorem is usually a squared plus b squared equals c squared. But let's use the variables. I'm using x. So x squared plus b we'll say is y. So y squared equals c, which we'll say is z. So we'll have x squared plus y squared equals z squared. So this is an equation that relates all these letters. All right, so that's usually the main one that we use with links for right triangles. And then our third step in these problems is to take the derivative. It's using implicit differentiation with respect to time. Okay, and we know we're doing with respect to time because we see the per second here, or we see the word rate, or the feet per second. So those are clues. And so now let's take this derivative. So its derivative is 2x. And remember, as soon as you do the derivative, just attach dx dt to it, or d whatever dt. And then we have plus 2y, and then we would attach dy dt equals, now derivative of z would be 2z, and then dz dt. Okay, so there's our derivative. And then now our fourth step is to plug things in. Okay, so we're going to plug in stuff. Plug in numbers for the variables. For some variables. Some we need to solve for still. Okay, so that is the 4-step process that was on the other page, just broken down for this problem. All right, well, let's see what we have. All right, so we have 2x dx dt. Now in here, let me go ahead and highlight. I have x is 8. So that's when I want to start plugging these numbers in. Okay, so the x is 8. So I'm going to plug that in. So we have 2 times 8. We'll highlight. Keep it color-coded. And then dx dt, I have it marked in red in my picture, so let me keep it in red right here. So that will be a number. And they told us, well, dx dt is this number 4. So it says the bottom of the ladder is sliding away from the wall at 4 feet per second. So this is 4. And I have to think, well, should this be positive or should this be negative? Well, the distance from the wall to the bottom of the ladder is increasing. So the distance is increasing, so that means this should be positive. Okay, so we've got distance increasing, so dx dt is positive. Okay, so it should be 4. Okay, so let's put that down as 4. So now I'm starting to put numbers into my variable picture because I'm really kind of done with it. I'm just starting to plug everything in. And then we have plus 2 times y. Well, y, I'm going to highlight in the maroon or in the pink. Y we found with our number picture as 6. So we'll sub that in. So y is 6. And again, I'll just keep my color coding going. And then dy dt, I have it marked in blue. So I'll put it in blue here. But that's what they want us to find. They say find the rate at which the top of the ladder is moving down. So they're saying find that dy dt. So let me add that note right there. That's what we're finding. So that means that's what I should keep it as my variable. So dy dt is just left as dy dt. And then equal to 2. And then z, well, z is the length of the ladder. Let's go ahead and use one other color. I'm going to do it in green. So that's z right there is 10. So we have 2 times 10. And let me make that 2. Let me keep my colors. Oops. I'm going to just make it consistent. So that 2 there we go. So 2 times the green 10, z was 10. And then dz dt, well, dz dt I don't have anywhere yet. Okay, but let's make a note of it. dz dt is something special. Let's do that in purple. So we'll add a little star here. Well, dz dt is special. dz dt will be 0. Okay, the reason for that is, well, notice on our horizontal, the x would change length as the ladder slides away. So the closer it is to the wall, the smaller x is. The farther away from the wall, the bigger it is. And similar with y, when the ladder's sliding down, y itself is getting smaller. Okay, so y is changing depending on where the ladder's sliding. However, z is never changing. It's always 10. The ladder is always 10 feet long, so no matter how it slides, it stays 10. So it's never increasing or decreasing in size. Okay, so z never increases or decreases in size. So that's why the derivative is 0, because these are explaining the change in those lengths. So this, again, this cannot change, so that means it just stays 0. Okay, so dz dt, so here we have a special case, it's 0. Often that happens. So usually if you have a ladder problem, unless they say specifically that the ladder, say maybe it's like one that can telescope or something that extends, then you could start to use those numbers. But otherwise, it's usually assumed that the ladder's not changing sizes. So that means the change in the length of the ladder. So that's what this represents. This is the change in the length of ladder. Change in length of ladder, well, it's again never changing, so it'd be 0, which makes this now problem much nicer. Okay, so we'll plug in the numbers and then now we'll start to solve. Okay, so we plugged in all the numbers. We have 2 times 8 times 4. Okay, so this all multiplies and it gives us 64. And then we have plus 12 dy dt, and then equal to 2 times 10 times 0 is 0. And so I want to solve for dy dt at this point, so that means I would subtract 64 over. So I have 12 dy dt equals negative 64, and then I would divide by 12 on both sides, and we'll get dy dt equals, well, negative 64 twelfths, that does reduce. Those are each divisible by 4, so it looks like it'd be negative 16 thirds. And the y unit, okay, so let's get our unit on there. The y unit is in feet, so the length of the wall is going smaller, but it's in feet. And it looks like the time unit is second, so negative 16 thirds feet. Oop, my pencil might not like me to write anymore. Let's see if, there it goes, feet per second. Okay, but let's also put it in words. We'll finalize it. So this is a change in the length of y. The negative is telling us the ladder is sliding down and getting closer to the wall. Okay, so we have the change in y. We could say the vertical length. Okay, so the change in the vertical length is, I'm going to keep it as a fraction, is 16 thirds, or is, sorry, with the negative, let's put is decreasing at 16 thirds feet per second. Okay, so it's sliding down, so that means the vertical length from the top of the ladder to the bottom is decreasing. Again, the negative, and notice on my word statement I don't have negative here anymore. The decreasing is taking care of that. So the change in the vertical length is decreasing at 16 thirds feet per second. Okay, so that's it. Well, if you have any questions, please let me know. Otherwise, thanks for watching, and I'll see you again next time.